Use Newton's method to approximate a root of the equation, boom, as follows. Let x1 be the initial, find x2, find x3, there they are. So how do we do this? Well, here's Newton's method. Newton's method says x2 is x1 minus f of x1 over f prime of x1. That's Newton's method. Where that formula comes from, I'll show at the end of the video for those who are interested. But for now, I'm just going to show you how you use it to answer for that function. There's my function right there. That's going to be my f of x function. We want to take that function and find a couple approximations to roots. All right, how do we do it? Well, what we basically do is we're going to go to our home page of our Canvas course right here. And on the home page, I put in a new link. There it is. That's the Desmos graphing calculator. The one down here is the Desmos scientific calculator, but the one up here is the newly added Desmos graphing calculator link. So if you click on that, it'll open up a graphing calculator link. So let me show you that. There it is. So there's what it'll look like. Now I typed in the function on the first line. So there's the function, the 2x to the 7th plus 4x to the 4th plus 2, and then it graphed it for us. By the way, this thing, so here we go. Or on the second line, I'm going to expand this to the right. Give me some room here. And then I'm going to go add a little plus sign up there, a table. I go up to the top, and I'm going to make that n. You go to the next spot, get rid of that, make it x. Next spot, make it f of x. Next spot, make it f prime of x. And the last spot, I'm going to make it x minus, I'm going to do the Newton's formula here, f of x divided by f prime of x. There we go. And then I'll put a 1 here, go down, put a 2, go down, put a 3. That's all we really need. My first x value, it said, here, I'll show you. If you remember, it said start at, right here, oops, there, x equals 1. So x1 is 1. So x1 is 1. And there's our function, which I just typed in. All right, back to it. So you just put a 1 in there for your first x value, and boom, it automatically populates. And then that 0.733333 number, that will go down here on your next line, zero point 0.7, and how many threes is that? A bunch of threes. It's just threes forever. You can just type a bunch of threes in. There we go. And then this next number, so I'm just repeating the number on the far right every time. 451151, and boom. And we can really stop right there. Let me just take a picture, bring it over, show you what I'm talking about. We basically have our answers. Here we go. There it is. So this right here, this is our x1, this is x2, and this is x3. So really we had it right here. We could have just stopped right there. So every time I just take this number, bring it to the next line, take this number, bring it to the next line. And it's an iterative process. It just keeps repeating the same thing. And so there's our x3. So they wanted x2, it's a 2, and x3. Let's make sure we had those right. X2 and x3. There's x2. There's x3. We got it. So that's all you have to do. Now, so that's the end of the problem. Type those in, you're good. Now, let me talk about what is it doing? What is this? So we type basically this formula and this Newton's method formula. And what's it doing? Well, it's actually finding the zeros. It's actually, now you think, what do you mean the zeros? Well, it's trying to find this spot right here. Now, where is that spot? Well, this looks like it's back -1 right there, -2 there, here's -3, -4, right? So it looks like it's between -1 and -2, right? Right here, it's at -2.98. So you think, what is it really? Well, let me show you another screen. Here's where I did it further. Now, you don't have to do it, but I just want to show you how this process works. Here's the same beginning we had. Here's the third one. I went all the way down to the 12th one. And by the way, I clicked on the graphing calculator, and it told me its approximation. There's the root. We call that a root or a zero or an x-intercept. Those are all different names for the same thing. It's an x-intercept because it's where it hits the x-axis, right? This is where the graph hits the x-axis. It's a zero because the height is zero there. Why is it called a root? I don't know. That's just another name people use. So that's a root, x-intercept zero. Anyway, and when I click on it, you can click on it right on the Desmos graphing calculator. It'll tell you its estimate, -1.32472. And it makes sense between -1 and -2, as we said. Well, look, down here by the 12th, that's what the 12th entry, it had it. It had, well, here, well, I should not there, right here. Look at that, -3 point. Man, I thought it had 247. Oh no, right here. I'm sorry. This one. Yeah, that is the one. Yeah, see how that's the same as that? 3.247. That's even more. It would round to two. There it is. So it eventually gets it. And usually a lot quicker than that. So Newton's method, notice, starts out at point 0.7, point 0.3, and then it gets really accurate. It's correct out to what, 1, 2, 3, 4, 5 decimal places. It's correct. That's what your calculator does. Calculators use Newton's method in computer programs that solve things. Their internal programming is this method, basically. That's what this thing, Desmos, just did. It did Newton's method. And here we are by hand, well, by table, doing Newton's method and getting the same answer. That's what Newton's method is. All right. That's all you need to know. For those interested, you can keep watching this video and I'll tell you where Newton's method comes from. Like, what the heck is Newton's method? How did he come up with that? Let me show you. So here is the backstory. Newton's method is based on the idea that if you have a curved graph, you can find where that thing hits the x-axis, the root, the zero, the x-intercept, whatever you want to call it, using the idea of tangent line projections. So start at some point x0, here's the point, and find the tangent line and let it go till it hits the x-axis. Then go up, find another point, take the tangent line right there and hit the x-axis. Boom, find another one. See how we're walking closer and closer and closer to the root? That's what Newton thought of. It's a genius method. So that's the idea with Newton's method is you just keep doing the tangent line, hit the x-axis, next tangent line, x-axis, next tangent line, x-axis. It's like the tangent line aims you towards the root, and then the next tangent line aims you closer to the root, and the next tangent line aims you closer to the root. You just keep following the tangent lines. They're like signposts leading you to the root. Now you might wonder, okay, why do we need all this, Mr. Heron? I mean, can't we just if this is some kind of function, looks like an x squared function. Say this is 3x squared plus 2x minus 7. Can't you just set it equal to 0 and solve? Can't you just use the quadratic formula, the negative b plus or minus the square root of b squared minus 4ac all over 2a, where this is a, b, and c? You're totally right. You could, if that's a quadratic. It's not. Remember, it's x to the 7th or something. So it's not a quadratic, even though it sort of looks like it in this part of the graph. Or this is just a made up thing. Oh, yeah, I'm getting lost. The problem we were working on was x to the 7th. So yeah, if we have x squared, there's a formula. If you have x cubed, there's a formula called the cubic. It's really, really complex. If you have x to the 4th, there's actually a formula called the quartic. Crazy complex. X to the 5th and beyond, there's no formula. In fact, not only do we not have one right now, there never will be a formula. They've proven there never could be a formula for x to the 5th power and higher. I know that sounds weird. Like, how could they prove there isn't one? How do they know they just haven't found it? Well, there's a whole area of math called existence proof, so they've proven it. There never will be an x to the 5th or higher. So my point is, you can't solve everything the normal way we do things, like with formulas. This is not going to work. And not only polynomials, how about if you have an equation like sine x minus x equals 0? How about if your function is, sine x minus x? How you gonna find out where that's 0? Think, oh, you can do it. Just add the no, you can't. It's not going to sine x equals x. then what? Just do the sine inverse. No, you do sine inverse. Yeah, it'll take care of that side, but now all of a sudden you got sine inverse over there. How do you get that x alone? You can't. So my point is there's all kinds of equations in the real world when we do engineering, math, science, that we cannot solve using formulas. So, and never will be able to. Never going to exist a formula for fifth degree or higher. All right, so then what do? We do Newton's method. So that's why Newton came up with this. It's a way of approximating. It's a numerical approximation method. And so I'll just give briefly what he did is he just said, well, here's the equation of the tangent line right there. Then he just took that tangent line and he went till it hit the x-axis. So he took that right there and he plugged in for x, x1, and he set it equal to zero because he wants to know when the height is zero, when the y value is zero. And then he solved that equation coming down here. He solved for x1 and got that. Here, maybe I'll just show that part of the puzzle. How would you solve this for x1? We'll move this to the other side. So then we get f prime of x0 times x1 minus x0 is negative f of x0, right? And then let's let's divide. What we're trying to solve. Oh, we're trying to solve for x1, aren't we? So let's distribute. Boom to boom. So f. Oh no, let's divide. My mistake. Let's divide both sides by f prime of x0. F prime of x0 is a negative here. Boom boom. Then we get x1 minus x0 is negative f of x0 over f prime of x0. And then you get it. Just add over. It becomes plus x0, right? So there it is. There's the formula. X1 is x0 minus f of x0 over f prime of x0. So they just solved it. So that's what Newton did. So he just took, this is the tangent line equation up here. Then he just plugged in x1, where is it equal 0, found that the next place you're going to hit the x1 value is that. And then the process just continues, right? So x1 is x0 with this stuff, then x2 is x1 with this stuff, etc. Any n value is the previous with that stuff, and you just walk closer and closer to the root. So that's Newton's method. It's a genius method. And there we go.